Now, having studied about the parameters A and B, we now come to the Z versus P curve for a real gas. Now this curve, the straight line which you can see, which is yellow in color, is the one for an ideal gas. An ideal gas has Z equal to 1. However, for non-ideal gases, Z can be greater than 1 or it can be less than 1, right? Because for non-ideal gases, Z is generally not equal to 1. So if you observe at very low values of pressure, let's look at this part of the curve. So if you observe this part, this one, the pressure is very low. Like if we go even closer to the axis, and at very low pressures, the gases all tend to Z is equal to 1, right? The limit at P tends to 0, Z tends to 1, which would mean that at low pressure, ideal gas behavior can be seen. And we had already concluded that. Now, if you look at some of the graphs, let's first look at the graph of hydrogen. Hydrogen is this light blue colored graph. And similarly is the graph for helium as well. Let's draw a graph for helium also here. This is what the graph for helium looks like. Okay, the white colored one. Now, for hydrogen and helium, their Z, if you observe, is always greater than 1. Right? It is never going into the range of Z less than 1. This means that they always show positive deviation. And it also implies that they are generally incompressible. Remember, the plots here have been plotted at the room temperature, that is 25 degrees Celsius. So at 25 degrees Celsius, hydrogen and helium do not show negative deviation. They are incompressible. But when we reduce the temperature, they will show negative deviation, right? Then if we talk about the other gases, such as carbon dioxide. So carbon dioxide is this dark blue one. It shows negative deviation first, and then after around a pressure of 500, it starts showing positive deviation. What does that mean? This means that when the pressure is less than 500, carbon dioxide can be compressed. It is compressible by applying pressure. However, when the pressure increases beyond that range, the repulsions among the molecules come into play, the factor B. It comes into play and does not compress the molecule further. And now, due to the repulsions, the compression becomes expansion. And therefore, Z is greater than 1 in the higher pressure ranges. And if you observe in the high pressure ranges, the Z for all of these is generally greater than 1. And from this curve, we can conclude one very important thing, that negative deviation implies liquefaction. Because negative deviation would mean that the V real, we go by definition, Z was what? PV real divided by PV ideal. So at a particular pressure, we can say that if Z is less than 1, then V real is less than V ideal, right? Which implies that there has been compression, and compression would in turn imply liquefaction, that the forces of attraction have come into play and the gas has been liquefied. So let's see what significance do these Vanderwaals constants A and B have in liquefaction. If you remember, A was a factor which contributed for the pressure change, right? It was the pressure correction term. And the pressure was corrected due to the intermolecular forces. Correct? That was why the pressure decreased in a real gas. So we can say that A is proportional to the intermolecular forces. I'm calling it IMF here. So we can also say that higher the intermolecular forces, higher would be the liquefaction. So in turn, A is proportional to liquefaction. So as A increases, the intermolecular forces increase and liquefaction also increases. So we can say that for a polar molecule, let's say water and ammonia, what can you think about A of each of them? Now, in a polar molecule, if we draw the structure, we have water here, right, with two lone pairs, and we have ammonia here with one lone pair. So the polarity for water will be high, the polar nature because of the orbital magnetic moment of water. So the polar nature of water will be high. Therefore, we can say that the dipole-dipole interactions for water will be higher than the dipole-dipole for ammonia. So since the intermolecular forces are higher, we can say that A of water will be higher than A of ammonia. And similarly, we can also say that A for any polar molecule will be greater than A for a non-polar molecule. Why? Because for a polar molecule, the force of attraction will be dipole-dipole, right? However, for a non-polar, it would be Vanderwaal's forces, which are weaker than the dipole forces. Next, let's move to the significance of B. Now, if you remember, B was the volume correction term. And so we can say that the size of the molecule will be proportional to B, right? Greater the size of the molecule, greater the correction we would have to apply. And we can also say that therefore B will be proportional to the molecular mass and to the size. And we can say that as the size increases, the van der Waal forces between the molecules increase, and therefore liquefaction would also increase. So for B, we can say that basically it is proportional to the size of the molecule.